All right. Okay. So, well, it is 5th week Wednesday, and um, we'll keep our lecture going on here. All right. So we've got on Monday we talked maximum likelihood estimation. Okay. I guess we're only in the 2nd chapter of the textbook, but I feel like I'm covering things well. And then we took the detour on neural networks, which I don't regret. And anyway, this is what we've got going on. Okay, so this is what we said on Monday. We said we are going to look at kind of multiple linear regression, and in multiple linear regression, we say that the data values that we have, the observed data, will be assumed to come from a normal distribution centered at our predicted value. So our predicted value is the product of our weight matrix W. So W transpose in each vector for observation n. So W transpose X of n. We've got a normal distribution centered there with a variance sigma squared. Okay. And if we say each value is normally distributed, then the total likelihood of all observations is going to be the product of their normal probabilities. Okay. And so if we take the normal probability density, it's going to be the product of all of these normal PDF values. Okay. And so so here's the likelihood is the product of everything. And we said, what we want to do is we want to take the derivative of the likelihood and set it equal to 0. And taking the derivative of product is hard, so we deal with the log likelihood. We take the log of this whole thing, and that turns the product into a sum. And then we say, okay, well, these are all a bunch of constants. And when we did that, we solved for the W that's going to maximize the log likelihood, and we got this solution. The solution is X transpose X inverse, X transpose T. That is the same solution for W hat that minimizes the... Sorry, what's going on? That's the value of W hat that the same solution that minimizes these sum of squared errors. Okay, and so maximizing the log likelihood is going to be equivalent to minimizing the sum of squared error. Okay, so this is where we left off on Monday, and what we want to do is we want to say, okay, what if I want to maximize the function with respect to sigma squared, or to the variance, right? So what value of the variance will maximize the likelihood? Okay. So this is the solution for what value of W will maximize the likelihood of the data. And now we have, okay, well, let's just treat W hat as our estimate, and we're going to treat that as fixed. And now the question is, what value of sigma will maximize the log likelihood function? Okay, so here I just plug in W hat into the log likelihood function, right? So that it's the same log likelihood function, this exact log likelihood function after I expand everything out. And all I'm doing is I'm replacing the W with W hat, okay? This part's negative n over 2 log 2 pi minus n log sigma minus 1 over 2 sigma squared, and this thing, that's all I got, right? Negative n over 2 log 2 sig pi, and okay. So I'm just replacing this with W hat, and I'm saying, okay, what value of sigma will maximize this log likelihood function? So I'm going to take the derivative of this with respect to sigma. Okay, this value is a constant with respect to sigma, so its derivative is 0. The derivative of n log sigma is going to be n over sigma. And then, and this is basically 1/2 sigma to the negative 2, okay? 1/2 sigma to the negative 2. When you take the derivative of that, okay, the -2 comes down and cancels out with the -1/2, and then it becomes sigma -3. So 1 over sigma cubed. And then, and this thing is basically a constant with respect to sigma, so I just bring that whole thing down as a constant with respect to sigma. So this is the derivative. I'm going to set that equal to 0, and I'm going to solve for sigma. I set it equal to 0, and I add n over sigma to both sides, and then I multiply both sides by sigma cubed, and divide both sides by n, and I get basically the value of sigma squared that maximizes this is going to be this quantity, okay? And what is this quantity? This is equal to the mean squared error, of your model, okay? Let's see. Yeah, exactly. All right. So you recognize that this is equal to the mean squared error of the model. So the MLE, the value for the variance, and sorry that the text is overlapping here. The MSE value estimate over variance turns out to be the mean squared error of the model. Okay, and so that's what we've got going on. Okay, and all right, so let's go ahead and take a look at what the log likelihood is at the maximum, right? So if we plug in the sigma squared into the maximum value, sorry, this should be a w hat here. This is what we're going to get, okay? So I just replace sigma squared with sigma squared hat, okay? This whole quantity right here is basically this. So we can say this whole thing is sigma squared times n, okay? So this whole quantity becomes n times sigma squared, okay? And then sigma by itself can be replaced with the square root of sigma squared hat, okay? And that's going to be, so I plug in log of sigma squared hat here, and to take the square root, that's basically raising it to the 1/2 power, and so I can multiply the log by 1/2. And so so here we get the log likelihood to be equal to this, and we get this quantity here, okay? And right here, this sigma squared hat cancels out with this sigma squared hat, and so I get -n/2. I got -n/2 log 2 pi, -n/2 log sigma squared, minus n/2, and I can factor out the n/2, and here I've got basically a constant, and here I've got -n/2 log sigma squared. I mean, I could factor out the n/2 even further, but I'm just going to leave this here. Okay, but okay, so what we end up seeing is that maximum likelihood, okay, this is the log likelihood, and at the maximum, and we can increase the likelihood function, or the log likelihood function, by further decreasing this value, okay? Because I've got a negative, there's a negative constant, -n/2, in front of log sigma squared hat. And so if I decrease sigma squared hat, you know, this value will keep shrinking, and multiplied by a negative, it will just keep growing then. And basically my log likelihood will continue to increase. And so, you know, if we think about what that means, sigma squared is the variance of the error in the model, okay? And so, you know, if you always think of the data as, you know, your prediction, the model's prediction plus error, you know, sigma squared is the variance of that error term. And so it's going to be the leftover variation after the model makes a prediction, okay? And so one way you can decrease the amount of error is to make the function that makes your prediction as complicated as possible, right? So if you keep making your prediction function more complicated so that there's less error, then you know, the remaining error will be as small as possible, and then you'll maximize your likelihood function. Okay, and so so that's what we can do. What we can do is, you know, so many of these things are related, is that we can maximize the likelihood by reducing the error. Okay, but if it means using a highly complex model, we also recognize that may not be the best idea here. Okay. Okay, so all I've done so far is I've just kind of worked through maximum likelihood estimation to come up with an estimate of sigma squared hat. Okay, and we said, oh, that turns out to be the mean squared error, MSE. And now we're talking about this, and we're saying, if you look at the log likelihood function, you can maximize it by making your model more complicated. Okay. All right. So so I'm going to cover the bias variance trade-off. This is a section from a lecture back in week 3 that I never got to. So I think at the end of Monday's lecture in week 3, I didn't get to it, and so I copied and pasted it into here, and I'll cover it here now. Okay. So so here I'm going to talk about the bias variance trade-off. Okay, and if you do if you search the internet for bias variance trade-off, you're going to see all of these pictures. This is like, it's like these 3 pictures are almost the same, and they're all going to look like this. It's going to have a curve for bias, and it's going to go down. It's got model complexity. As model complexity goes up, bias goes down. As model complexity goes up, variance goes up, and it says the total area is going to be basically, you add the bias squared and the variance, and you get something like this, and you want to get a model right here. Okay, so this is like this nice little picture, and we feel like, okay, that, I guess that makes sense. That's good, right? And you got, basically everyone has their own version of this picture, and they all look very similar. And so I wanted to kind of delve into that and show you some pictures here. Okay, and so you know, you could also read up on the Wikipedia page on bias variance trade-off, and that gives you this thing. The expected value between this and this squared is this. And so our expected prediction area is bias squared plus variance plus sigma squared. And I'm, I guess, dodging some math here, but we'll kind of look at it visually with some models. All right, so let's talk about each of these terms. The expected prediction error refers to the total squared error between the actual values and the predicted values for a new data set. So a new data set that you haven't seen yet, okay? That's going to be the expected prediction error. It's we're not talking about the error in your observed data that you used for training, because you can keep shrinking that by making your model more complicated. What we want to know is, how well is this model going to perform on new data that we haven't seen yet, okay? And so this error is going to be, you know, the difference between y minus y hat squared, and we want kind of the expected value of that. Okay. The bias is the expected difference between the predicted values and the actual value for new values of x. Okay, so this is what the bias is going to be. We want to know for predicted values and the actual values for new values, okay, of x, what is there going to be a difference? So with something like linear regression, or you know, bias means in the long run, the value will the average, the expected value is equal to the true value, right? And basically, if the average of your predicted values is equal to the actual value, then you have no bias. But if the average of your predicted values is different from the actual value, then you're going to have bias. Okay. The variance is going to be the variance of the predicted values. And sigma is the standard deviation or the noise in the generating data. So let's take a look at this, okay? I asked the other class, and a handful of students said they learned local or Loess regression, and I just kind of want to check with you guys. How many of you learned local or Loess regression? No? Okay. All right, so a bunch of you are saying no. Okay, all right. Okay, then that's fine. Then I will talk about this here. I don't want to get into it too much, but it's kind of like, it's a little bit like a moving average. You guys are familiar with like a moving average, yes? Okay, so with a, so it's kind of like a moving average, except it's like a window. So generally, you know, you'll talk about a moving average like as the days go on, it'll say like basically the average of the past 7 days. But with local regression, basically you're taking kind of like a moving average of like the three. You have like some point here, and you look at like the 3 values to the left and the 3 values to the right, and you take the average of those. That's kind of like a loose idea. Okay, you're technically doing a weighted regression on the local values, and so we covered like weighted regression in like one of your homework problems. What you can do is you can put higher weights on the values that are close. So if you have some value right here and you've got other points over here and other points over here, you can put higher values on the higher weights on the values close to your prediction point, and then as you get farther away, you can decrease the values. But anyway, one important thing to know about local regression is that you don't get a function, you don't get a y-hat function, you just get basically predicted values, and it's just done by kind of averaging and interpolating the nearby values here. Okay, and there's some control parameters for the Loess curve, and inside R you can use this function Loess, and it's going to perform basically local regression, and you can have it fit a smooth or a jagged line. Okay, a jagged fit will reduce the error, but increase the variance. Okay, so I'm going to start off by generating a true model. Okay, and I'm not going to bother explaining all of the code here, but the true model is going to be this quadratic line. Okay, the quadratic line represents the true model in the population. So there is a relationship between x and y, and it's dictated by this quadratic line. Okay, and to simulate our situation, what I'm going to do is I'm going to take values along this true line, and I'm going to just add some random noise. Okay, so I'm going to take 21 evenly spaced values, so basically 0, 0.05, 0.1, 0.15, so on and so forth, up to 0.95 and 1.0, and I'm going to add some random noise to it. And then to those data points, the randomly generated data points, I'm going to fit a straight line. Okay, and so that's what these lines do. Basically, I generate some errors. The true values, this is the quadratic part. I add the random normal errors to that, and I'm going to get my observed y's here. And I'm going to plot that, and then I'm going to fit a linear model between the observed y and the observed x. And I'm going to plot that as well. All right, I hope you guys can see this. So I probably should have picked a different color. In light gray, these are the randomly generated values, okay? So they are generated around the mean, okay, or around this red dotted line. The red dotted line is the true relationship, and I added random noise. Sometimes the values are higher, sometimes the values are lower, sometimes they're right on the line, and there's very little error. And I want to fit what I've done is I fit a straight line to these randomly generated points. Okay, and so even without the underlying dotted line, we could see, okay, this straight line doesn't do a perfect job of fitting our values. Okay, So the model that we produced, that straight line model, is going to be wrong. Okay, at best, even at its best, the linear model simply can't fit a quadratic function. Okay, and the difference between the model and the true relationship is going to be the bias, right? And then, but that might still be okay, because if you draw a new sample, what you're going to have is you're going to get low variance in the predicted values. Okay, so you're going to get a new sample of data. The new sample of data is going to be different from the other sample, and you'll fit a different line. Okay, and so basically I've done the same thing. Okay, all right, and in this plot, again, the true relationship is the dotted line, and I've just generated new random errors, new noise, and that's going to be the purple dots. And what I've done is I fit a straight line to the purple dots. Okay, and I've done the same thing this time with orange dots. Okay, so again, I generate values around the true relationship, and so we've got random noise around the true relationship, and I fit a straight line. Okay, so here is random points, and I fit a blue line to the points, random points, and I fit a purple line, random points, and I fit an orange line. Okay, and if I overlay the fitted lines, this is what we see. We see there's actually the amount of variance between the predictions that the blue line, purple line, and orange line make is fairly low. They're not exactly the same. Each one is different because they are subject to the random noise in their particular data set, right? So each of these were, we estimated the slope and intercept based on different random data sets, and because the different random data sets are random and have noise, our slope and intercept aren't exactly the same. But overall, there's not too much difference between the blue, orange, and purple lines. Okay, they're quite similar to each other. Okay, so I'm going to do something similar. Okay, except this time, instead of fitting a linear model, I'm going to fit a Loess curve. Okay, local regression, and I use span equal to 0.25, and what that does is it makes a very wavy, jagged line that is going to overfit the data. It's going to have very little data for the observed, or I'm sorry, very little error for the observed data, but it's going to have, but it's going to be overfitting it. Okay, so here is our randomly generated data. Okay, and this blue line represents what we fit. Okay, so we fit a curve to the randomly generated data, and it looks like this. And so so that's what it looks like. Okay, very little error in the observed data set. Okay, but just visually we can say, oh yeah, we're definitely overfitting the data. Okay, yeah, there's a tiny bit of error here and there, but very little error for a data set, but we can tell that we're overfitting it. Okay, I do the same thing. Okay, I do the same thing with a new random data set. So I generate some new random data points, so 20 new random data points, and I have I fit another Loess curve that overfits. Okay, and again, we get very little error between the Loess curve and the generated data. Okay, and then I do it right here, and we also get another line. And if I overlay the blue, purple, and orange lines, then this is what we get. Okay, and what we see is that there is a lot of variance, okay, a lot of variation between what the blue, purple, and orange lines will predict. Right here, for this value, the orange line predicts a low value, whereas blue and purple predict something closer to the true value. Over here, orange predicts way up high, and blue and purple are lower. Over here, orange and purple predict something close to the true value, but blue's prediction is way off. Here, orange is close to the true value, but blue and purple are off. So anyway, and we've got a lot of variation between what the blue, orange, and purple lines predict. okay? You know, you compare that to this, okay? For right here, orange, blue, purple are all over the true values. You know, over here, orange, blue, purple, you know, there's variation between them, but they're all underneath the true value and things like that. So there's not a ton of variation between orange, blue, and purple here. Whereas over here, there's a lot of variation between orange, blue, and purple. Okay. So when we compare these, okay, when you look at these things, if we were to take the average of orange, blue, and purple, if we take the average of orange, blue, and purple, we actually might get something close to the true model, which would indicate low bias, okay? But because the predictions that they make from one model to the next is very, very different, that indicates high variance. So, so that's an undesirable trait. Okay, I just wrote a wall of text, but basically I'm going to do the same thing that I've done here. Here I generated 3 random samples, and for each sample I generated, or I fit a model, right? I'm going to do the same thing, but I'm going to do it 100 times, okay? I'm going to generate 100 random samples, and for each 100 random samples, I'm going to fit 100 models, okay? So, so this is all the code. I'm going to just skip over it. You can read through it if you want, but that's what we're going to do. Okay, so here is what happens if I fit a bunch of linear models. Okay, let's explore this. Okay, this black line represents the true quadratic relationship. The true quadratic relationship is this thing. Okay, and again, what I've done is I've generated 100 different random samples of data centered at the true relationship. 100 different random samples of data centered at the true relationship. And for each of those different random samples of data, I fit a different linear model, okay? And all of these, this rainbow road, okay, is basically all 100 different linear models that we fit, okay? Most of them are concentrated in this kind of central path or highway. Yeah, we've got a few, there are a couple lines that are kind of, you know, a little far off, but most of them are very close to each other, indicating that there's very little variance from one predicted model to the next, okay? Sure, there is some variance. They're not all exactly the same, but the amount of variance from one model to the next, especially kind of in the central region, is very low, okay? These white dots represent the average of all 100 lines, okay? So if we take the 100 lines and we average them, we're going to get a white dot right here, okay? If I average all of the predictions right here, I take all of these 100 lines, and I say, what value did you predict for right here? And I average them all, we're going to get a dot right there, okay? And what we can see is that these white dots, this is the expected value of our predictions. The white dots represent the expected value of our predictions. They are not close to the true relationship. Okay, as far as the true relationship goes, the expected value of our predictions are quite far off. Okay, we've got this value is pretty far away from the true relationship. These values are pretty far away from the true relationship. So we've got high bias indicating that in the long run, the expected value of our predictions is not going to be close to the true relationship. Okay, maybe right here it is, and maybe right here it is, but in the long run, you know, these values over here are going to consistently be too high. These values down here and these values over here are going to consistently be too low. In the long run, I can't expect my expected value of the predictions is different from the actual value. Okay, let's look at, so that's what we got. The white dots do not fit the true relationship well. That's high bias. The different colored straight lines don't drastically vary from each other, right? So these, there's a bunch of straight, different colored lines, but they overlap quite a bit. So that indicates low variance. Okay, let's look at this thing. Okay, so this is a crazy picture. All right, so this thing of spaghetti is, we got rainbow spaghetti here. What's going on is I've got 100 different Loess curves. Okay, I fit 100 random Loess curves, and not random Loess curves. I'm sorry, I got 100 different random samples of data, and for each random sample of data, I fit a Loess curve. Okay, that Loess curve overfits the values a lot. Okay, and so we have a ton of variation, right? Okay, so right here, for this location, we've got, one Loess curve fits up here, another Loess curve fits here, some are over here and in between and all the way down here. We've got a ton of variation for all of the different Loess curves that fit this value right here, okay? But if I take the average, of all of these things, I get this white dot, okay? So the white dot is the average prediction value of all of these different spaghetti lines, okay? Like if you look at this point, this dark blue line predicted super low value, and this light blue line predicted a super high value. But if you take the average of all of the values from here to here, they all kind of balance each other out, and you get this white dot, okay? So these white dots represent the average of all of our predicted values, okay? And what we can see is that they end up following the black line, the true relationship, quite closely. It's not perfect, okay? It's not perfect. We still have a little bit of difference between the average expected value, the average of the predicted values, and the true relationship, but they follow it pretty closely, okay? And so all up and down the graph, that's what we have. We've got, if you look at the white dots, they follow the black line fairly closely, but the individual lines show a ton of variation from one to the next, okay? So that is going to represent low bias, okay? White dots fit the true relationship well, that's going to be low bias, but the different colored lines vary drastically from each other, so that's the high variance. So the linear model was high bias, low variance, okay? The white dots don't fit the true relationship well, but the variance between predicted lines is low. But then the spaghetti lines for Loess have low bias in that they fit the true relationship very well, but there's a lot of variance from one model to another, okay, or one fitted value line to another, and so that's what we have here, okay. And ideally, we want to achieve some kind of balance where we have low bias, not too much bias, and not too much variance. And so this would be a Loess curve with something in between, okay, not that uses some values, and in this case, the average values, these white dots, fit the true relationship quite well. And then as far as variation goes between one model to another, it's pretty there's not as much variation, right? The models are all fairly close to each other. Yeah, you get every now and then you get a line that kind of sticks out, but overall the amount of variation is fairly low. So that's the idea between the bias variance trade-off. So this is, I guess, something somewhere around here where you don't have too much bias, you have fairly low bias, and your variance is also fairly low. Okay, that's what we're hoping for. Okay, so that's the bias variance trade-off. This slide represents what I've just said. Okay, so let's we're going to continue on here, and we're going to talk about Fisher information. Okay, did you guys learn Fisher information in one of your classes? Which, yes, okay. Which class covers Fisher information? And what do you guys remember of Fisher information? Okay, 100B. 100B covers Fisher information. All right, okay. So everyone's saying 100B or 101B and 100B too. Okay, and what do you guys remember of it? Okay. Well, I don't know. All right. Well, we'll start covering Fisher information in today's lecture, and I'm certainly not going to have enough time to get through all of these slides and get through the whole concept. Maybe Fisher information is a tough concept, okay? So I'm going to just kind of I'm going to simplify it and give you kind of just the easy version or big idea of Fisher information without getting too much into the theory. I mean, there's still going to be derivatives and calculus and all of that, but basically, we're going to first start talking about derivatives, and then we'll get to Fisher information, I guess, on Friday. So today we'll just talk about derivatives and second derivatives and stuff like that. Okay, so if you think about a univariate function, okay, just a regular old univariate function, you know, your Calc 31, Math 31A and 31B and stuff like that. What you learn is the derivative is the slope. It's the rate of change of a function. Is the slope high, you know, and stuff like that, okay? And then the second derivative is a rate of change of the slope itself, right? How quickly does the slope change? Does the slope change rapidly, or does it change slowly as you're going over the function? Things like that, okay? So if you have a large second derivative, that means the slope changes rapidly. That means you're going from, in one moment, you're going, you have a very high positive slope, and then very quickly, it changes to a high negative slope, okay? So that would indicate a large second derivative, okay? If you go from high positive to very negative slope, it changed rapidly, which means the second derivative is very high, okay? On the other hand, if you have a very gradual change, right? Your slope is slightly positive and it becomes a little bit less positive until it becomes 0 and it's flat, and then it becomes slightly negative and slightly negative, then you have a small second derivative, okay? And then the other thing that the second derivative tells you is the concavity of the function, right? So if you know that you have a first derivative equal to 0, so you're at some critical point, either a min or a max, then if you have a positive second derivative, okay, then you have a local min, because a positive second derivative means you started off with a negative slope. The slope becomes less and less negative until it becomes 0, and then the slope becomes more and more positive, indicating that it's it's concave up and you have a local min, okay? A negative second derivative means you started off with a positive slope. The positive slope becomes less and less positive until it reaches 0, and then it becomes negative and more negative, indicating you've got a local max, okay? And then if you got a second derivative equal to 0, then maybe you've got an inflection point or something like that. That's your review of univariate functions. Okay, so I think all of you guys are familiar with that. All right, we have kind of the multivariate equivalent of the derivative, and that's the gradient, right? And so here, what we have is we have some function that goes from n-dimensional real space to one real number, right? So we've got a function like the loss function. The loss function takes in a vector of parameters, right? You've got, like in the in linear regression, sorry, you got a vector of w's, a vector of weights, okay? Or even in the neural network, you've got some loss function that takes in a bunch of parameters in n-dimensional space, and then it maps it to a single loss value, right? You've got You go from n-dimensional real space to one real number, okay? And when you take the gradient of the function with respect to a vector, to kind of that input vector, then the gradient, okay, nabla f, is going to be a vector of the partial derivatives, okay? Each component it's the derivative of the function with respect to the first component of the vector, derivative of the function with respect to the second component of the vector, all the way to the derivative of the function with respect to the last component in the vector, okay? So you get a gradient, right? And we can think of this as kind of the multivariate generalization of a derivative. Okay, we can do this and get a second derivative, all right? So the second derivative, do you guys remember what that would be called? The second, if I take the second derivative of this gradient, what am I going to get? We call it the Hessian, okay? So if you take all of the second order partial derivatives, okay, then you get the Hessian matrix, okay, which is going to be an n by n matrix. We kind of remember this. All right, and so this is a matrix of second order derivatives, okay, and you can kind of think of it as the multivariate generalization of the second derivative, okay. And so if we take a look at each column in here, it's going to look something like this, right? So the gradient is the derivative of the function with respect to w1, and then derivative of the function with respect to w2, all the way to the derivative, partial of f with respect to wn. And then so the Hessian is going to be the second derivative with respect to w1. Oh, I have not mentioned the quiz answers. They are D and A. Today's quiz answers: D as in dog for the first question, A as in apple for the second question. I'll go ahead and do that. I got a couple minutes left. D as in dog, A as in apple. So those are your second quiz questions, or first and second quiz questions. Okay. So here's the Hessian matrix, and basically we're going to take this thing and we're going to basically ask, what is the gradient of this component, right? And so the gradient of this is going to be a n-dimensional vector, a vector of length n, and that's going to basically fill out this column. Okay, so it's going to be the derivative, partial of this with respect to w1, which will become d2 dw1 squared. Okay, what's the partial of this with respect to w2? That's going to be d2f dw2 dw1, right? What's the partial of this with respect to wn? Okay, that's going to be d squared f dwn dw1. Okay, and then we do that for this one. What's the partial of this with respect to w1? And you're going to get d2f dw1 dw2. Okay, and this is going to be symmetric. These two are going to be equal to each other, so this is a symmetric matrix. Okay, and you get the partial of this with respect to w2 is going to be basically the second derivative of this with respect to w2, so on and so forth until you get to here. And so you get an n by n matrix of second order partial derivatives. Is that all right for the Hessian? Okay, so what we can do with this is that we can kind of decide if something's concave up or concave down, okay? So again, with the univariate function, the sign of the second derivative, right, whether it was positive or negative, told you if it was concave up or concave down, okay? And for a multivariate function, then the definiteness, I don't know if that's a word, okay, but the definiteness of the Hessian matrix can tell us about the kind of the curvature of the function, right? And so, so if you have the gradient of the function is equal to 0, I guess this should be the 0 vector, at some point x, and the Hessian matrix is positive definite, okay? And so if you guys remember what it means to be a positive definite matrix, then that means, any vector times the matrix times the vector will be positive for all values. Or another way is all eigenvalues of the matrix are greater than 0. Okay, if you have a positive definite matrix, then the function is going to be concave up, and x is going to be a local minimum. Okay, if you have a negative definite matrix, okay, then the function is going to be concave down, and you've got a local maximum, right? So if you have a two-dimensional function, concave up would look kind of like a bowl, and if you have a negative two-dimensional function, negative definite would look like a hill. Okay. If you have both positive and negative eigenvalues, then you've got a saddle point. Okay. Maybe it's concave up in one direction and concave down in the other direction. Okay, so it's something that looks like a saddle. And then if you got eigenvalues equal to 0, then you're going to need more information to determine concavity here. Okay. All right, so we're going to run out of time for today. But like the second derivative of a univariate function, a high second derivative will tell you that you've got a high change in the slope, which indicates very high curvature. And the same idea can be applied to the Hessian matrix, which is kind of our multivariate generalization of the second derivative. And it can be used to tell us how confident we are in our parameter estimates, which will get reflected in the Fisher information. So we'll end here for today, and we'll continue on Friday to kind of continue talking about the Hessian and Fisher information and all of that. Okay, so we will we'll end here, and we'll see you guys on Friday.